Hey folks, we got another example of motional EMF. This one's a little more complicated than the previous one, but not that much. A little more math. While you're sketching this out, let me describe the situation. You've got the rails that we had in the previous problem, a magnetic field. This time the bar is going to start from rest, and we're going to pull with a constant force F naught. And that could be anything, and I'll discuss that in a sec. But for now, it's just you pulling on the bar. And you're going to keep that force steady. And a quick reminder, the EMF generated in that bar due to its motion is negative BLV. And again, the negative is just about direction of the motion of the charge. We discussed that already. And then the magnetic force, resistive force is that. So as the velocity of the bar builds up, that resistive force builds up. All right, so if you need to, pause the video to sketch this out. All right, we're back. All right, so let's say that you start pulling the bar from rest. As you continue to pull, the velocity builds up and this resistive force gets bigger. And eventually the resistive force is going to match your pulling force and the bar will stop accelerating and will move with a constant terminal velocity. So a couple of our goals here. One is to find that terminal velocity. But two, we're going to find the velocity of the bar as a function of time. And actually, I'm going to start with finding the velocity of the bar as a function of time, and then the coefficient out front will be our terminal velocity. To find the terminal velocity, though, all you would do is set FB equal to F naught, and then solve that for velocity. That'd give you your terminal velocity. So just like in the previous example, we're going to figure out the motion of the bar, we're going to start with Newton's second law. And that is net force equals ma, right? And as you pull the bar to the left, you're going to build up this resistive force to the right. So now we have two forces in our problem. We've got an F naught minus F bar, okay? And that equals ma, okay? F naught's a constant force. The F of the bar, or F magnetic field on the bar, is B squared L squared V over R, and this equals M, and then of course A is dV dt. So again, got the classic differential equation first order. We got V and its derivative in the same equation. So we got to separate our velocity from our time. So now it's a little bit of algebra here. So basically what I'm going to do for the algebra, is there's a lot of ways you can do this. I try to get it so that the V doesn't have any coefficient in front of it. So I'm going to multiply it by the reciprocal of this fraction, all three of my terms. So my first term is F naught times R over B squared L squared. Then I got to minus V, and that equals Rm over B squared L squared dV dt. Okay. And then I am going to do several things at once here. So this is a term I'm going to keep together. I am going to divide both sides of the equation by that entire term. So I'm going to have a dV over V. And then I'm going to take the reciprocal of this. I'm going to multiply both sides of the equation by the reciprocal of that. When we do that, we get the following equation. You get dV over F naught R over B squared L squared minus V equals, and then over there you get a B squared L squared over Rm dt. Okay, now we're ready to integrate the left side and the right side. Now the right side, time goes from 0 to t. We're starting our watch and we start pulling. The left side, this time the velocity actually did start at 0. You actually started from rest. Thank goodness. It makes the problem easier. So we got a 0 and we're going to some final V after a certain amount of time. So when you integrate this, you get, and I'll write this down bottom left here, you get, and I'm going to use my natural log rule, so I get natural log of, and you're going to have a nice big term here. If we plug in V in for this, you get F naught R over B squared L squared minus V all over. If you plug in 0 for that, you get F naught R over B squared L squared minus 0. And that equals, on the right side, you just get B squared L squared over RMT. Oh, and Mr. Mashar had one goof here, okay? When I integrated this, you have to do the natural log, you have to have something in the denominator and its derivative in the numerator. What do we forget? We forgot our negative sign. The derivative of negative v is negative dv. So I am going to add that in right there, and I got to multiply both sides by -1 to do that. So this right side down here becomes a negative. Okay, that's important. Otherwise, we get a nonsense answer. All right, now we're going to take the exponent of both sides, and then I'm going to multiply both sides by this denominator here. And so you get f naught r over b squared L squared minus v equals the same thing, f naught r over b squared L squared e to negative b squared L squared over rm times t. And then if you get v by itself, you do a little algebra, you get velocity as a function of time is equal to this coefficient, f naught r over b squared L squared times 1 minus e to the negative b squared L squared over rm t. And we've had that kind of expression many times before, different constants in there, but the same kind of expression. If you were to graph this velocity as a function of time, our max terminal velocity is this coefficient out front here, f naught r b squared L squared. So I'll just write that as v max, okay? And we start from rest and we exponentially decay toward that value. Now, some notes on this. First note is depending on different problems, you might have different f naughts. So in this problem, we call it f naught. If you have, let's say, a bar falling vertically, then f naught would just be mg. If you have a bar falling on an incline, which you're going to see a few problems like that, then your f naught would be mg sine of theta. So you got to kind of see like what is your f naught, okay? Now, on that vein, the next example, I'm going to kind of tweak this slightly for f naught, and then I'm going to talk about a shortcut that you can use to solve these first-order differential equations that have a constant out front here. So that have a constant and the variable and then the dv dt. So I'm going to recreate that on the next example and show you a nice shortcut. Signing off for now.